We have two types of spatial information. We have raster data, which is represented by pixels, and we have vector data, which is represented by points, lines, and polygons. Pixel data is based on a square pixel and a grid of these pixels. So a 25-meter grid of pixels will have more detailed information than a 250-meter pixel size grid, because the information shown in each pixel is the average of what is occurring on the ground. So for 250 meters, all of that information is amalgamated to represent just the dominant value in that area. So smaller pixels, more detailed information in your raster. Larger pixels are more coarse, less detailed information. Examples of raster grids or raster information is your elevation, your land use, your aerial imagery, soil grids, and also climate data is often represented as raster information. In contrasting raster, we have vector, which have points, lines, and polygons. This is much more detailed information because the information hasn't been averaged over an area as it has for a pixel. Points are just that, they show us a specific XY location. Lines may be straight, they may be curvy, they may have lots of little lumps and bumps in them. But as long as the lines are open-ended and do not enclose an area, lines are considered line data. Polygons, by contrast, are lines that must enclose an area to be polygon information. So a polygon is an enclosed area. If you were to map your paddock boundary and basically not shut the gate or not join the points where the gate is or the lines, you would have an open area where the lines do not join to make an enclosed space, and that would be line data. However, to calculate an area or to represent areas, you must have a closed space, which is a polygon data. So examples of polygons could be your land parcels or your paddocks. Line data is often roads or railways, and point data is often specific point information such as customers. So on this slide, in the map here, we can see that our raster data is made up of our aerial imagery, which could have been obtained from either airborne, such as a plane, or it could be obtained from satellite imagery. This is raster data. If we were to zoom right in, we would see that that image is actually made up of pixels. Our polygons are our paddock boundaries, our lines are our waterways, and we also have point data shown on this image as well. When we produce a map, there are several essential map elements that actually make the map a map as opposed to just a diagram. So every map has a title beginning at the top. Every map has a north arrow, which shows you which way is north. Every map should include a scale bar, which shows you what distance on the map is equal to what distance on Earth or on the ground. So if you have a centimetre on the map, does that equal a centimetre on the ground, which would be a 1-to-1 map, or does it equal a metre on the ground or a kilometre on the ground? We also put in our projection details, such as Mercator or WGS 84 Mercator projection, that sort of information. Every map should also have a legend to explain what is being represented on the map, and the production details, who made the map, when. And along with the production details, we could also have any copyright information as well. The aerial imagery should also be referenced where appropriate. So if it's being downloaded from the web and it has copyright as to Google or Bing Maps or Google Eye or various other PSMA agencies, all of that information needs to be included on the map as well.
In this particular slide, we will discuss map resolution, which refers to the level of detail shown in a raster map. The level of detail shown in a raster map is based on pixels and pixel size. Whenever a pixel is shown on a map, it is actually showing one value for that particular pixel area. So if the pixel area covers 1 meter, it will find out the average value for that 1 meter squared, and it will present that as just one value over that 1 meter squared. If that area that the pixel covers is then a 10 meter square area, again it will average all of the information within that 10 meters squared and present it as just one value. So what we find is that small pixels will provide a more detailed image because there is less averaging of the information that they represent. That is, each within a 10 meter squared, you would have 100 pixels, 10 by 10 pixels, instead of just 1 pixel. So you would have 100 times the information in a raster that has small pixels compared to a raster that has large pixels. So what we say about pixel size is that where you have a large pixel size, you have a low resolution because you have less detailed. The information is coarse and blocky. Where you have a very small pixel size or a smaller pixel size in comparison, you have a higher resolution raster. And this is because you have more pixels for a given area, you have less averaging of the information, so you have a more accurate representation of the information, and therefore it's more highly detailed. So small pixels have a high resolution, more accurate representation. They're not as chunky sort of representation of the image. Low resolution is large pixels and chunky information. Map scale refers to the areal extent of the information shown on a map. So this is referring to how wide or how large a geographical area is portrayed on a map. So on the right there are two map images. One is an image of Australia, which covers a large areal extent, a large geographical region. And below that is a sample farm map, which covers a much smaller geographical region than that of Australia. So when we refer to scale, we refer to the level of detail that is shown. So a small scale map covers a very large area, but it shows a very low level of detail. In the map of Australia, we can't see as much detail as we can see on the farm map. And typically a small scale map is represented by 1 unit on the map. Here we have a scale of 1 to 500,000, so 1 unit on the map is equal to 500,000 units on the ground. And those units could be 1 centimetre on the map equals 500,000 centimetres on the ground, or 1 millimetre on the map equals 500,000 millimetres on the ground, or 1 inch on the map equals 500,000 inches on the ground. The units on both sides of the scale ratio are the same, but a small scale map typically has a much larger, very large number on the right hand side. A large scale map, in contrast, covers a much smaller area, geographical area, and this enables it to portray more highly detailed information. So therefore we would be able to see boundaries or infrastructure or road networks much more clearly. And with respect to scale, the number on the right hand side of the ratio is typically much smaller. It could be 50, it could be 100, it could be 1 to 125,000. It's generally a much smaller value than a small scale map. This slide here just portrays a trick that you could use to determine if you think your map or a map that you are looking at should be a large scale or a small scale map in comparison to another map. Typically, the issue is confused that a map of Australia should be a large scale map because it's showing a large geographical area, and typically a farm map should be a small scale map because it's showing a small geographical area, when in fact the description is actually the other way around, as we discussed on the previous slide. Now, one way to remember this is that in a ratio, if you have 1 to 500,000, if you then divided that ratio, 1 divided by 500,000, this would produce a very, very, very small number. On a larger scale map, the number on the right-hand side of the equation is typically smaller than that on a small scale map. So 1 to 50. If you have 1 divided by 50, it gives you 0.02. Now, in comparing these maps, 0.02 is much larger than 0.000002. So, our large scale map is our farm map, and our small scale map is the map of Australia. Remembering that a ratio of 1 to 1 represents real world size, so that is a very large scale map because 1 divided by 1 gives you a value of 1. Again, those numbers with the division, they don't actually really represent anything in particular. It's just a trick to remember. If you were to divide it and the number you get is very, very small, you have a small scale map. If the number that you get is closer to 1, you have a larger scale map. There are many different sources of data that we can use within a geographic information system. One of the questions we need to know is that, is the data that we are using for our analysis or for creating our maps, is it relevant and is it appropriate for the purpose for which we wish to create our map? To determine this, we look at metadata. Every spatial information file should have metadata associated with it. And metadata is basically your Word document or your printed text that provides you with information about the spatial data. So metadata is simply information about the spatial data. Metadata typically comprises of the who, when, where, how, and maybe the why. So with respect to a spatial data set that you are either looking at using or sourcing or maybe even purchasing for your analyses or for your mapping, the metadata is available online to allow you to assess whether the information that you're seeking is appropriate or not. So the metadata will include who collected the data, whether it be an individual or an organisation, when the data was collected and over what period of time. Some data collection takes years, many, many years. Others might be a short-term survey. They might detail how the data was collected and also the maintenance of the data. Is the data current for a short period of time, and therefore the data set is not going to be continually maintained or updated? Or is the currency more temporal and requires regular updating? There should be information in the metadata about how often the data will be updated and when that may be expected to occur. The metadata will cover the geographical extent of the data, so the area that it covers, and these will typically be described in terms of coordinates. Further metadata information will follow on the next slide. So metadata will also describe the validity of the data, under what conditions is the data and the use of the data valid and invalid. There will also be licensing requirements with respect to that. You may have to personally contact the custodian, who is the person responsible for that data set, and ask permission to use the data. You might have to sign a license agreement regarding how the data will be used and represented and referenced and acknowledged. You may have to purchase the data from the custodian, and with that purchase sign a licensing agreement. The metadata should also provide information with respect to the resolution of the information, and also the custodian, which is who owns the data, who maintains it, who provides the licensing, and the who regarding the contact details on who you contact to purchase, use and obtain the information.